In this problem, we're asked to determine the cross slope at station 44. To see the actual details, we're going to need to zoom in, but just to orient us a little bit here, we're going to look for this portion of the curve for station 44. So now that we've zoomed in a little bit, we're going to review a couple of key values and factors that we're going to need to use to solve this problem. And I'm actually going to solve this problem two ways. I'm going to start with the fastest, the quickest way, and you may see this if you work with a problem like this before, and then I'm going to solve in a more kind of complete and classic way using the relative gradient profile. So a couple of points we're going to need to know: the point of curvature, the PC. It was labeled here on the highway design plans, station 44 plus 81.65. We can't see that label because I'm zoomed in. These are design plans from the North Carolina Department of Transportation, and so there's some things that are specific to certain agencies, and I'll point out a couple of these that may be specific to NCDOT design plans. Your assumptions may need to change if you're using other states or jurisdictions' plans. And another value that's important is this increment of 50 feet. And what this tells us is how far you need to move along the distance in the center line to have a 1% change in cross slope. And so we can see that in several areas. We can see here as we're changing from 2% over to 1% cross slope. That's going to be a distance of 50 feet that's required to make that transition occur. NCDOT uses a 1/3, 2/3 method for locating the PC and PT of the curve. What this essentially means, if we take this PC point here, 1/3 of the super elevation transition is going to happen past that point, and 2/3 happens before you reach the PC. So on a curve that has a design super elevation of 4%, the PC at the PC station, we're going to have a cross slope of 2/3 of 4%, which is 2.66%. So we can really solve this problem with the information we have here. I'm going to summarize it here, and then again, as I mentioned, we're going to go to that relative profile gradient as well. So we know station 44 is 81.65 feet before the PC. That's just based on the math. The PC is at station 44 plus 81.65. Going back to station 44, which is our given point of interest, that's going to be 81.65 feet. The inside lane is at a 2% cross slope at this point, and the outside lane changes 1% of cross slope for each 50 feet that's traveled. So if we have our cross slope at the PC is 2.66%, and we're going to go back 81.65 feet, that's going to change the cross slope by 1.633%. So we get that by dividing the distance traveled, 81.65 feet, by that 50-foot increment. And essentially what we find here is that we have 1.633 increments of change. Each increment is 1%, so we have 1.633% change in cross slope moving from our PC back to our point of interest, station 44. And so the cross slope for the outside lane at station 44 is 1.03%. We get that by taking the cross slope at the PC, 2.66, minus the distance traveled, percent change to 1.63%, gives us that 1.03. So that's the solution to this problem. We're going to work it out in a longer format. We're going to get the same value, but you can approach it different ways and still find the correct value here. So this is our traditional profile view, looking at that transition for a simple curve. We see this 2/3, 1/3 runoff at the top of the diagram here, along with that PC, and we're going to just move through this diagram looking for the points of interest that we need and solving for the value, finding those final values we're looking for at station 44. There are multiple ways to work this. I'm only showing one approach or one way to move through this diagram. Obviously, there are multiple ways, correct ways to solve this as well. Our PC, this was a given, station 44 plus 81.65. We're going to have 2/3 of the runoff coming before the PC and 1/3 of the runoff coming after. In different jurisdictions, this distribution can change. This is what we're going to use for this problem. The super elevation runoff, that total distance, is from the adverse crown remove, which we show as point B in this diagram, to the full design super elevation point D. The design super elevation is 4%. And an important value we're going to use for the way I'm going to show how we're going to solve it is that 2/3 of the runoff. The full super elevation runoff is 200 feet. We know that because we have a design super elevation of 4%. To go from adverse crown remove, which is at 0, up to 4%, that's 4 increments of 50 feet. 4 times 50, 200. So 200 times 2/3 is 133.33 feet. So to find the station at point B, we're going to take our PC station, subtract that 133.33 to get a station of 43 plus 48.32. That means we're moving in the right direction. 44 is going to be past this point, so we established a good point at point B. Now we can establish what the station is at point C. We're going to add the tangent runout. The equation for tangent runout is the normal crown over design super elevation multiplied by runoff. In this case, we have normal crown, which is 2%, design super elevation of 4%, so 2 over 4 is 1/2, so it's going to be 1/2 the runoff. The full runoff is 200 feet, so half of 200 is 100. So we're adding 100 feet to point B, and that's going to give us a station at point C of 44 plus 48.32. That's great news for us. Now we know that our station 44 is between points B and C. This is adverse crown removed and reverse crown, so we know our point is there. This should really help us. This diagram should really help us. At this point, should be very confident that that inside lane is going to be at 2% super elevation. We haven't started that transition after reverse crown to where the inside lane is actually rotating. So we're not rotating the inside lane at this point, so we know that's 2%. What we need to solve for is the outside lane. And what we're going to use to do this, we're going to use similar triangles. So here's our large triangle, and so we're going to use that coming up on the next slide, and we're going to try to find the smaller triangle here, the dimensions of that, using that larger triangle, using that similar triangle. So we know station 44 is 51.68 feet from adverse crown removed. We need to move 51.68 feet from adverse crown removed to meet our point of interest, station 44. Based on the length of the tangent runout, which is 100 feet, the inside lane is at 2% cross slope because it's between adverse crown removed and reverse crown. The outside lane takes a little more work, a little calculations using similar triangles. Our large triangle has a Y value, that vertical component of 4%, that's our design super elevation, and the runoff, or the X value, is 200 feet. We're looking for this smaller triangle that we've already established. That X value is 51.68 feet. That's the distance from adverse crown removed to our point of interest, station 44. And we need to solve for what I have labeled here as Y. So we can set up an equation for this. 4% over 200 is Y over 51.68 feet. That's going to give us a Y value of 1.03. That matches the value we got previously. And so the final answer here, the inside lane has a 2% cross slope, and the outside lane has a 1.03% cross slope.